All right, everybody, we got this one last question. So it's coming back in to wrap up some of that missing pieces of stuff from thermochemistry that we didn't learn because we hadn't approached equilibrium yet. But now we've approached equilibrium, and so we can sort of get a handle on what's going on with with uh, reactions under non-standard conditions, or when the reaction quotient does not equal the equilibrium constant. So we get this question. It says we allow this reaction to proceed, and then we find that the concentration of all of the products and reactants is 0.525 molar. So we want to calculate the delta G of the reaction at that time, not the standard, not the delta G naught of the reaction. We want to know the actual delta G, the free energy change of the reaction at that moment in time. And so what we need to do is use this formula. Delta G of the reaction at this moment in time equals the standard free energy change for the reaction plus RT natural log of Q. So it could be at a different temperature, or I could have different concentrations. Now, in this case, I'm at the standard temperature, 298. I'm going to go ahead and use 298.15. We're going to get the same numbers. But the reaction quotient is what's different. Now, remember that the reaction quotient is still the concentration of the products raised to their stoichiometric coefficients divided by the concentration of the reactants raised to their stoichiometric coefficients. So I can rewrite now delta G for the reaction equals the delta G given, negative 71.2 kilojoules per mole, plus RT natural log of Q, and R is 8.314 joules per mole Kelvin. Temperature given 298. And now I need to write down the natural log of Q. So the concentration of every species is 0.525. So I'm going to go ahead and stick that in, 0.525. That'll be squared divided by 0.525 quantity squared times 0.525. Now, this particular problem happens to be able to be simplified fairly easily because 0.525 squared divided by 0.525 squared is 1, so that goes away. So it ends up just being the natural log of 1 over 0.525. And so I want to rewrite all of this down, and then let's go ahead and do that calculation. That natural log is 0.644. All right, so let's continue to simplify. I'm going to do this multiplication. So I get 8.314 times 298.15 times 0.6444, and I get 1,597.35 joules per mole. Now, I want to point out something. This is in joules. That's in kilojoules. We need to have them in the same units to do the addition. So I need to change this one on the right to kilojoules. So that'll be 1.597 kilojoules per mole. And now when I add them together, I get delta G for the reaction equals negative 69.6 kilojoules per mole. Okay, so now we've got the delta G for the reaction. The next part of the question was, is the reaction at equilibrium? And if not, what direction will it proceed to reach equilibrium? Well, remember that it's not at equilibrium because at equilibrium, this is the point that we were trying to make recently, the delta G of the reaction is 0. The spontaneity of the forward and reverse reaction is the same, so the delta G of just the forward reaction is 0. Now, we know that it's not at equilibrium because delta G has to be 0 when it's at equilibrium. So which way will it proceed? Well, delta G is still negative, right? Remember, when delta G is negative, the delta S of the universe is positive, and so the reaction is spontaneous. And so that means it's spontaneous as written. And if it's spontaneous as written, then what's going to happen? That means it's going to proceed from left to right, from reactants to products. It's going to shift right towards products. And so that's the direction it goes to reach equilibrium. Okay, that's it.